Hey folks, how we doing? All right, getting started here on recording our week 2 notes. Okay, so as you can tell from the topic, on the Canvas site, we're going to be talking about ideal gases and real gases. So I hope that gives us a little bit of familiar ground, right? Hopefully you remember some of this stuff from Chem 109. If not, we're going to review some of that here today and then expand on that into the new stuff. All right? In the meantime, we'll just let this nice My Morning Jacket get us started. Okay, folks. So, equations of state. So the concept of the equation of state is it is an equation that can describe the physical state of a substance. And so as an example, I can say pressure, P, is going to be some function of T, V, and N, where, of course, pressure, P for pressure, T for temperature, V for volume, and N for number of moles. And so this equation describes 4 variables. So P, T, V, and N. And the idea with the equation of state is if 3 of these are specified, let's say, if 3 are specified, then 1 is fixed, right? So if we explicitly define temperature, volume, and number of moles, pressure has to be fixed for those set of conditions to give us that state, that equation of state. And so, of course, an example of this that hopefully you all know and love, P equals nRT over V. I know you wanted me to say real bad, PV equals nRT. I want to say it like that too, right? We've memorized PV equals nRT, right? But in the spirit of this equation of state, I can say P is a function of TV and N, which then of course equals nRT over V, right? So let's write that, I should say P, right, as a function of T, V, and N, okay? So more into the equation of state of pressure, or just pressure in general. So I talked about this on our first lecture. Pressure is force over area, okay? Oops, and I'm already getting sloppy on my notes here. I'm running out of room. So, right, and one common unit of pressure that you're probably all familiar with, pounds per square inch, right? That's a force per area. But, right, remember our SI unit here, sorry, I didn't give myself enough space, is the Pascal, okay? And 1 Pascal, recall, equals 1 Newton per meter squared, or simply kilogram meter per second squared when we take the definition of the Newton, right? So the standard units, and we're gonna have to get used to this term standard. We're gonna see this in this class a lot. And I'm gonna put in parentheses P0, because when we see that superscript 0, we should recognize now that as standard. Okay, we're gonna see that in a lot of things. So standard conditions of pressure are bar, okay? And so 1 bar actually equals 10 to the 5th Pascal, okay? So it still has the same base unit, but it's just 10 to the 5th of these, okay? And so other units, right, the more common unit we are aware of is the atmosphere, and 1 ATM equals 1.01325 times 10 to the 5th pascals. So you can see an atmosphere and a bar are very closely related. 1 atmosphere equals 1.01325 bar, okay? So other units that we get are also the torr, okay, and which we recognize that is 760 millimeters of mercury. And where does that come from? Well, that comes from this idea of mechanical equilibrium, okay? So suppose I have a reservoir here that I'm going to draw. All right, okay. Forgive my drawing. Let's try that a little bit better, okay? So there's just our reservoir. There's some liquid in it, in this case, some liquid mercury. And suppose that we then also have a column, okay? And that column is closed, but then open on the bottom. And the idea here is the atmosphere pushes on the liquid, right? The force due to gravity is pushing on the liquid, okay? Which in turn pushes this up. Of course, this liquid is also getting pushed down, so it obtains this mechanical equilibrium. It obtains some specific height, okay? And I'm not going to derive this equation, right? But we know that if we were to go through and do that, we would recognize we could measure the pressure of the atmosphere from this force getting exerted on this liquid by the density of the liquid, rho, times gravity, times the height of the liquid, okay? And if this liquid is mercury and we're at sea level, right, then that's going to be 760 millimeters above the other liquid surface, okay? And this is given for Galileo's graduate student, Torricelli. Okay, so the Tor is named for Torricelli. So we recognize that that gives us 1 ATM. Okay? All right, so let's see. I have a little bit extra on mechanical equilibrium in my Fall 19 notes, but I think this is pretty sufficient. So I'm going to move forward. Okay, so let's talk a little bit about temperature as another state, right? As another variable that we can use in the equation of state, okay? So two definitions with temperature that I want you to know, diathermic and adiabatic. So diathermic means thermally conducting, and adiabatic means thermally insulating, okay? And I want you to get used to these terms, okay? A diathermic container, for example, or an adiabatic container. So here I have my like super fancy, expensive Yeti mug. Is this diathermic or is this adiabatic? What do you think? It kept that water nice and cold. It's got to be adiabatic, right? It's got to be thermally insulating. It's not perfectly adiabatic. Go away, endpoint antivirus. So it's not perfectly adiabatic, and we'll talk about that as we progress through the semester. Okay? So now with thermal equilibrium, so this is kind of what I wanted to show you with mechanical equilibrium on the other side, but I think the idea of the barometer, right, I suppose we could go back for a second, right? On mechanical equilibrium, right, if I can exert more force on this, right, then the mechanical equilibrium says that this liquid level will have to go up as more force is being applied on this liquid level, right? It goes up through that way. But of course, if I remove some of that force, if I pump vacuum on this, or there's less atmospheric pressure that day due to some meteorological phenomenon, right, then the liquid level will go down, okay? So that's the mechanical equilibrium. So our thermal equilibrium goes as the following. So suppose that I have two containers, and this is a diathermic wall, okay? So here, if I have T1 and T2, and T1 and T2 are not equal, and of course a diathermic wall separates them, then eventually T1 and T2 will become the same temperature, okay? And so the idea is, if let's suppose it's this situation where okay, T1 and T2. If T1 is greater than T2, then heat will flow from T1 to T2, okay? So T1 will become a lower temperature, T2 will become a higher temperature. And of course, if it's the opposite of that, if T2 is greater than T1, let's make that a 1, then heat will flow from the hot object to the cold object, okay? So it's not that the cold, let's think of a good way to think about this. So heat will flow from the hot object to the cold object, okay? That's always true. And this is what gives us the 0th law of thermodynamics. And I'll read it for you and then I'll write it down, okay? If A is in thermal equilibrium with B, and if B is in thermal equilibrium with C, then C is in thermal equilibrium with A. Okay, so let's write that down. If A is in thermal equilibrium with B, and B is in, I'll say, thermal equilibrium with C, then of course A is in equilibrium with C. I know that looks terrible. I can't even read it. Please use the closed captions. Look at my Fall 19 notes. Listen to what I'm saying while I'm writing it. If A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. Okay, that's the 0th law of thermodynamics. Okay, so that's the simplest way we can start. So that's kind of more or less all of the general review I'm going to do on equations of state. From here on out, we're just going to be applying these equations of state. All right. So let's talk about the gas laws, right? Speaking of equations of state, right? So we know Boyle's law, and Boyle's law says P times V equals a constant at constant number of moles N and temperature T, okay? Charles' law says V over T equals a constant at constant N and P, okay? Constant number of moles and pressure. And then Avogadro's principle says V over N equals a constant at constant P and T. Okay, so now what do all of these mean? Well, we could rearrange this, right, algebraically, and we know really Boyle's law says that P is proportional to 1 over V, of course at constant T. Okay, so Charles' law says V is directly proportional to T at constant N and P. And of course, Avogadro's principle says volume or number of moles are directly proportional to each other as well. So here in Boyle's law, right, as the pressure goes up, the volume has to go down. Or as the volume goes up, the pressure has to go down. They're inversely proportional. But Charles' law, right, volume and temperature are directly proportional. So assuming that number of moles and pressure are held constant, if you increase the temperature, you increase the volume. You decrease the volume, you decrease the temperature. And similarly with the Avogadro's principle, assuming pressure and temperature are constant, then if you increase the number of moles, you have to increase the volume. And so now here we have our total equation of state, the ideal gas law, the combined law, which of course we know is P is a function of V, T, and N, which equals nRT over V. So the gas constant, R, is this constant of proportionality that allows us to combine all these laws. And really, it's not the gas constant, right? It's Boltzmann's constant, but you knew that, okay? So Boltzmann's constant is what allows us to combine all of these laws. And so now here, is a capture from your book, from Atkins. And I think this is pretty cool to see this gas law on this three-dimensional landscape, okay, P, V, and T. And we can actually point out the individual laws from this landscape. So for example, if we see PV equals a constant, here it is, right? Okay, so here is our Boyle's law, okay? And so that's P inversely proportional to V. So imagine this shape, right? Imagine how this looks on the three-dimensional graph. Imagine how that would look on a two-dimensional graph, right? So now Charles' law is V and T are proportionate. And so, by the way, sorry, Boyle's law gives us an isotherm. Iso meaning the same, isotherm, so temperature is constant. And we can see on this line, right, this is a line of constant temperature. Charles' laws gives us an isobar. So that's a line of constant pressure. And here you can see it's kind of tough because it's not on an axis that we're used to seeing. But if I were to take this three-dimensional graph and flip it up like this, right, so that I would have, let me see if I can even do that, a volume on the y and temperature on the x, then, right, we would see this constant proportionality. Whereas, right, Boyle's law, P over V, does this inverse relationship, okay? And then finally, the Avogadro's principle gives us, let's see here. It's actually, oh, Charles' law also, sorry, I didn't point out. If we fixed volume in Charles' law, then we also know P is directly proportional to T, assuming V is constant. Sorry, this is getting a little sloppy. So this, where did it go? This PT, this isocore, that's also a manifestation of Charles' law, okay? And so you can see at constant volume, pressure and temperature will increase directly. So two lines from Charles' law, excuse me, isocores as well as isobars, okay? And because we don't have a number of mole axis on this, the entire thing is really directly related to Avogadro's principle, because Avogadro's principle is what allows us to put together these laws, in addition to, of course, the Boltzmann's constant of proportionality. Okay, so now I'm going to move on, and we're going to do a little thought exercise. For those of you that had me in Chem 109, this might look familiar. It's the exact same thought exercise I asked you to do when you were in general chemistry. But it's still just as tried and true as ever. So I'm going to set you up this thought experiment, and I want you to pause the video and just think for a moment what these two answers should be. Okay, so suppose we have a container, and it's exactly 22.42 liters. We've put 273.15 Kelvin in this container. Don't worry about this container with H2O. Let's just focus on this container with helium for now, okay? And we put 1 mole of helium atoms. So we have a container. We put 1 mole of helium atoms. It's 22.42 liters, and it's 273.15 Kelvin. What is the observed pressure in this container? Okay? Is it... And I'll give you some ranges, okay? We'll just say, is it 1 atm? Is it greater than 1 atm? Or is it less than 1 atm? Okay, so think about what that is for this case of helium. Now, then let's talk about this other one. So we have the same container, 22.42 liters. We put 1 mole of water molecules in there, and it's 273.15 Kelvin. Now, I know you're chemists, and you're like, but it's going to condense. And you'd be right. Let's just ignore that for now, okay? Don't worry about the water condensing. Maybe we could say it's 273.17 Kelvin or something, okay? So don't worry about condensation. What's the observed pressure here? Is it exactly 1? Is it greater than 1? Or is it less than 1 atmosphere? Okay, so I want you to actually pause the video and think about that for a moment, okay? Okay, hopefully you paused. Hopefully you thought about it for a minute. I'm not going to pause. I'm going to keep going, okay? As it turns out, to 4 significant digits. I got 4 sig figs right here in the volume, okay? It would be 1.000, right? And hopefully you remember, we could calculate that even too, right? P equals nRT over V, okay? And we would get 1.000 if we were to calculate that. And of course, over here, we would get the exact same number because it's the same equation. However, what this equation of state is not accounting for is the fact that molecules interact and that they occupy volume. Okay, so we're going to get to that in a few more slides. I'm going to highlight the differences between the ideal gas and the real gas, right? But if you notice on this water, I've got here these oxygens pointing towards the hydrogens, right? Because there's going to be some intermolecular forces at play, right? You all know that. We love water and hydrogen bonding. It's all its capabilities. And so what this would actually do is make this pressure just a little less. I'm going to change that equal sign, and I'm going to make it a less than sign. It would be just a little bit less than 1.0. Okay, I won't put any sig figs on there yet, but we'll just say it will be a little bit less than 1.0. And that is because the observed pressure is a result of the gases colliding with the container walls, right? These water molecules are going to have a greater affinity for each other. They're going to suck each other in from the container, and the observed pressure would actually be just a little less than 1 atm. Okay, so how do we start to build that up? Okay, well, we can start to correct for what the ideal pressure should be by saying, well, this ideal pressure is going to be this observed pressure plus this whole chunk right here, okay, represents what I'm going to call a collisional term. And those of you that are remember your Gen Chem days, you'll recognize that this is part of the van der Waal equation, and I'm going to put that together in total. But specifically, this chunk A times n over v squared gives us this collisional term. It accounts for the fact that these molecules are interacting with each other, and that influences them to suck into each other and collide with each other more, and collide with the container walls less. Okay, these molecules are attracting each other in. And the size and magnitude of this A term gives us that effect. So for example, you notice helium, it does have a definite A term. It has a value for this collisional term, 0.0341 liters squared per mole squared. Okay, and if I plug in 1, and I should have put in sig figs, right? When you calculate this, you do get 1.000. I meant to indicate that on all these 1.0s, okay? You do, in fact, get 1.000 when you consider this 1 mole of gas. So, right, this is 1 mole of gas at 273.15 Kelvin. The ideal pressure we know is 1 for those conditions at STP, right? But the observed pressure would also be very close to 1. Same with neon. It actually doesn't change it all that much. But now, look, once you jump up to argon, argon's A term goes up almost a full power of 10, and now it starts to become noticeable. And we get all the way down to water, 5.46, one of the largest values. Chlorine's value is actually bigger. Gives you a pretty noticeable effect, 0.989 if you had a very sensitive pressure meter. Okay. And so what you might guess is at play here are the intermolecular forces. So for example, we know water and ammonia are capable of hydrogen bonding, right? Okay, so that's a very strong intermolecular force. As a result, they have a pretty large A value. So what's the deal with chlorine? Okay, well, as it turns out, chlorine has quite strong London dispersion forces because of that mess of electrons surrounding it, right? So those electrons can undergo instantaneous induced dipole in the vicinity of neighboring chlorines, right? And you notice here what happens with this collisional term, the more number of moles you have, the bigger the effect is going to be, right? Conversely, the more volume you have, the smaller effect this is going to be. So as you force these molecules to get closer and closer together by either making more of them, by putting more of them in a container, or shrinking the size of the container, they will have no choice but to get close to each other, start to interact, attract each other, and reduce their collisions with the outside container, thereby reducing the observed pressure. Okay? So also, another pillar of ideal gas that I'll summarize here momentarily. Okay? The ideal gas law does not account for the volume of the molecules themselves. Okay? So as it turns out, the molecules do in fact have volume. They have finite volume. And that's given by the B term. And if you look at these units, liter per mole, this would actually be, so if you took helium and you condensed 1 mole of helium, it would actually occupy 0.0237 liters. So that's 23.7 milliliters if you could condense a mole of helium. That's not accounting for the space between the heliums, but just condensing them all together. All right? And so then, right, if we know that the ideal volume is 22.42 liters in 1 mole, then we can correct for that ideal volume with this observed volume. All right? And so you notice in all of the observed volumes, they're just slightly bigger than the ideal volume, right? Because the molecules themselves are taking up space, okay? And so that's what that B term gives us. And it's kind of hard to distinguish a trend here with these molecules, but certainly if you go through the noble gases, you can see the periodic trend almost perfectly. Helium actually occupies more space than neon, and that's actually due to neon's nucleus, right? It has more protons in it, and it can suck in those electrons just a little bit tighter. But then now when we get up to argon or even krypton or xenon, you can see that those, the atoms are getting bigger, right? So they occupy more volume, okay? And then certainly like chlorine is fairly large at 0.0562. Water, surprisingly, is pretty small because water can actually cram together quite efficiently, okay? So moving on, let's all put this together, this whole correction, the correction of P ideal and the correction of V ideal into the van der Waal equation, okay? And I'm going to write it as a function of state function, P as a function of V, T, and N equals nRT over V, so looking kind of familiar, but now that's minus NB, okay? And then now we have to have that correction term minus the collisional term, over NV squared, okay? And now these V's and P's and T's that I'm putting here are no longer like ideal or observed, they're just the state, right? So this would be the volume of this state or the temperature of this state, okay? So we don't have to think of these anymore as ideal or observed. They just are those state functions, okay? I'm also going to introduce another concept to make our life a little bit easier, and that is called the intensive parameter molar volume. So remember, we discussed that volume is extensive. It depends on the amount. But I can make this an intensive property by ratioing it to 2 extensive properties. So for example, if I say V divided by N, so we know volume is extensive, number of moles is extensive, but if I ratio 2 extensive properties, I have now an intensive property. That's going to be V lowercase m, molar volume. Bless me. Okay, because I don't think anybody's going to be able to say that to me while I'm recording this video. Anyways, so now whenever we see this in this class, we're going to see this quite a bit. Okay, we're going to see this subscript M, So that's going to make us realize that we're talking about a per mole quantity, and it gives us the intensive parameter. And it also reduces the number of coefficients we need. Okay? So I'll rewrite this now down here, and I can say P as a function of molar volume and just temperature. Okay? And that's going to go as RT over Vm minus B minus A over Vm squared. So both of these versions of the van der Waal equation are perfectly legal. It's just a matter of how many states or how many variables you want to keep track of. Okay, so get used to seeing both versions of these types of quantities. Okay, and so as we said, A and B are the van der Waals coefficients. Okay, so the volume occupied by a sample of gas molecules, right, gives us, so volume occupied by a sample of gas molecules has to be V minus NB because we have to account for the volume of the molecules themselves, okay? And so this term gets subtracted out because we really do want to account for not only the volume that the molecules occupy, but the space between them. Okay, and we don't want to double count that space. And then, of course, the collisional term is this A over NV squared. Because now you notice here, if we did a unit analysis on this, we would actually find that this gives us a unit of pressure. Okay, so let me back up really quick. So the A term is atmosphere liter squared per mole squared, right? So if A is atmosphere liter squared per mole squared, and I multiply it by mole squared over liter squared, right? Those cancel, those cancel, those cancel, and I'm left with atmospheres. All right? And then, of course, as you can see, we know that B rather, had units of liters per mole. So if I multiply B by mole, then I just get to liters. All right. So I think that, yes, okay, so that's a pretty good place to stop this lecture. Okay. Yeah, moving on to part 2 momentarily.